Good, good afternoon, dear colleagues and participants of the DESSERT 2023 conference. And today I will introduce you with the research that named about one possible tool for analyze safeness of discrete dynamic systems. But first of all, let me introduce myself. My name is Artem Panchenko. I'm third year PhD student of School of Mathematics and Computer Science of Kharkiv National University. And the other author, it's Professor Grigory Zheltkevich. He's a Doctor of Engineering and PhD of Math, Dean of School of Mathematics and Computer Science of Kharkiv National University. Let's start from the very beginning, from the domain of our research. So we work with distributed systems of different natures, for example, distributed computer systems, where there are a lot of computing nodes perform the tasks in parallel, or for example the cyber physical systems where we have a nodes of two different nature, or it's cyber nodes, some kind of soft, and the physical nodes, some kind of tools, engines, etc. We work with the systems of two types. It's a deterministic, that's a system where we always know the second step, the next step of the system, and the random where we don't know the next step, but for each system state, have a probability distribution of the next steps of the system. And we work with a system with output. That's a kind of type of system when for each step we have some kind of just text in terminal, for example, about the state of this system. So in general, in our research, we work with discrete, distributed, deterministic or random systems with output. The main problem of such systems, it's first of all a high risk of failure because of this distributed nature. The second one, it's a high cost of failure. So we need to particular attention to safety and resilience of the system. And it's completely clear that it's extremely necessary to study the behavior of such system. And in the picture, you see a good example of distributed cyber physical system. We have a car autopilot system, and of course, it's completely clear that it's high risk of failure because of a lot of input data, and the cost of failure of this system, it can be even human life, driver or passenger of this car. So it's, as I said, extremely necessary to study the behavior and pay attention to safety and resilience of such system. As a methodology of research, we use a algebraic approach, and now I will tell to you the main points why it's a good choice for research like that. So one of the main reasons for using algebras in the modeling of discrete system is that they provide unified language to describe states and processes for systems of different kinds. The advantages of employing algebras lies in the capability to articulate management procedures for intricate data structures, and algebras also harness to formalize and structurize intricate facets of cyber physical systems and encompassing security, safety, and dependability. In a simple words, we need to use formal language to avoid some kind of bugs and errors, and algebras, for our opinion, is the best choice here. If you talk about the algebras for software verification problem solving, we need to understand following: that the reasoning presented above is interesting for complex system analysis. Such system is not ultimately specified. This uncertainty is the reason why the mathematical model of the system is based on non-identity and there is an idea supposes the existence of a general algorithm for fully automated software verification. But from the other hand, we have a Rice theorem that states the impossibility of such an algorithm. So if we assume that the transformational program specifies a dynamical transformation, then we understand the impossibility for studying this transformation in all details. In other words, if we talk about the big distributed system with a lot of nodes, it's completely impossible to collect the data about the current state of each node because it takes time if we talk about big network. And during the collecting data about the current state, the state of some nodes can changes. So we will never have the complete information about each node. This problem we need to care in our mind when we try to solve the software verification problem. In the article, we introduced the concept of eventual algebra that can be useful in such situations. So it's actually the main goal of our paper to present the construction of an eventual F-algebra that related to any F-algebra. Dynamical transformation of F-algebra gives us a method for forecasting the state of a system modeled by this algebra as a next step of system operation if we know the current system state. Applying F to the F-algebra gives a new F-algebra. That's completely clear. The carrier of this algebra is a set of states forecast of the system modeled by the original algebra. And the dynamical transformation of this algebra provides forecasting of the modeled system state at the second step of its operation if to know the state forecast at the first step. Long story short, and I will double highlight it in the conclusions, for some kind of practical systems that is necessary to study the behavior, it's not always possible to determine the final algebra. And for us, the final algebra, it's some kind of carrier of knowledge about the system behavior. And for this case, we propose to use the concepts of eventual algebra that we presented in the paper. About the construction of this eventual algebra, here in the slide you can see the diagram, and unfortunately the time frame that I have for the presentation, it will be not enough to discuss it and describe it in all details. So I recommend the dear colleges just to review the paper where it describe it in really deep details. But here in this diagram, trust me, you see the same, completely the same that I discussed in the previous slide, but just in diagram view, when we have the previous and the next step of the system. So as a conclusion, we can highlight following. In the paper, we introduced a novel approach to comprehending a discrete dynamical system. The pivotal aspect here is the standard procedure of connecting forecast with the observation. The mathematical equivalence of the standard procedure is represented by the enter function. Interestingly, the existence of the eventual algebra for any given algebra hinges not on the original algebra itself, nor the specific properties of the enter function defining the algebra type, but solely on the presence of sigma collimates in the underlying category. Eventual algebras can subsist in algebraic categories devoid on final objects. This becomes particularly relevant in cases like non-deterministic systems without constraints on the extent of such non-determinism. Long story short, if we have some kind of system, we model it via algebras, but everyone knows that in this case, we need to build the final algebra just to find the system behavior, system properties, but here it can be impossible. We know it, but introduced approach can be used in these cases with a construction, some kind of algorithms that we describe in this paper. We can use the eventual algebra to investigate the system behavior, and we'll have some results. Of course, we have some point to further research. First of all, let's find out whatever eventual algebra have universal properties. It's completely necessary to build mathematical models that can represent the big class of systems, and we will work over that in our further research. The second one is compute eventual algebras of systems, which are important for practice. So we will find some kind of practical case of systems that it's impossible to build final algebra, extremely hard to build that. And we will compute eventual algebras for these systems and find out whatever the functor eventual has adjoint functors. It's also completely necessary to this research. Thank you for your attention, dear colleagues. Thank you for the opportunity to introduce my research. Have a good day.